Okay, hi everyone. It's wonderful to see you again at Emerge. I'm E, a PhD candidate in systems engineering at Berkeley and the organizer of Emerge seminar. The weekly Emerge seminar is a dedicated platform for early career researchers who are pursuing academic careers, where we warmly welcome final year PhD students, postdocs, and incoming assistant professors to take this unique opportunity to present research, refine ideas, and build a community among peers working at the intersection of mobility, energy, infrastructure, and sustainability. Today, we are very excited to welcome our fourth eMERGE speaker, Dr. Nicolas Christianson from Stanford University. Nico is a Stanford Energy Postdoctoral Fellow and an incoming Assistant Professor of Computer Science at Johns Hopkins University starting for 2026. Nico received his PhD in Computing and Mathematical Science at Caltech in 2025, while he was supported by an NSF Graduate Research Fellowship and a PIMCO Data Science Fellowship. Before Caltech, Nico received an AB in Applied Mathematics at Harvard College. Nico's research lies broadly at the intersection of algorithms, machine learning, and optimization, with a specific emphasis on the development of new theoretically grounded algorithms and AI/ML methods for reliable decision-making under uncertainty. Much of his work is motivated by modern energy and sustainable challenges, with applications ranging from energy resource operation to sustainable computing systems. Today, Nico will talk about reliable AI-augmented algorithms for energy. And without further delay, let's join me to welcome Nico for his explanation.
Thank you, Yi, for that wonderful introduction. So I'm Nico. I'm going to be talking today about some work that I did during my PhD on reliable AI and machine learning augmented algorithms for energy. So uncertainty is a key challenge in planning and operating energy systems. And energy grid and resource operators face many different kinds of uncertainty, like uncertain and variable renewable generation. Oops, not sure how that happened. Uncertain and variable renewable generation. Yeah, that's not working. Let me try to just restart this real quick. Just try, okay. Uncertain consumer demand, unset asset outages, and strategic behavior on the part of market participants. And considering all of this varied and multifaceted uncertainty, you might imagine that AI and machine learning could help to get better performance and more reliable operation in energy systems. And we've all seen AI and machine learning achieve state-of-the-art performance in applications like game playing, language models, self-driving cars, and even some systems challenges like data center cooling. But there's one main challenge when deploying AI and machine learning to these high-stakes problems in energy, and that's that AI and machine learning typically don't have any kind of guarantees. And so we can't necessarily trust them when we deploy them. And so there's a lot of research over the last decade or so on different failure modes that AI and machine learning models can exhibit, like adversarial attacks, where if you perturb the input of a classifier just a little bit, you might misclassify a dog as an ostrich. A distribution shift, where maybe if you train in one particular training scenario, and then you try to deploy the model in a different scenario, like maybe you train a self-driving car during the day and deploy it at night, maybe it will make you go off the road. And recently, there's been a lot of interest in failure modes from larger models, like language models, thinking about hallucination and things like that. And these are all pretty bad if we're faced with systems where we have significant reliability needs, like planning and operating the power grid. And so this motivates the broad research theme of how we can design reliable AI and machine learning methods to advance sustainable energy systems so that we can get better performance, hasten the clean energy transition, but also make sure that we're not going to suffer any significant risks as a result. So my research tries to tackle this question using an approach that blends theory and practice And so on the one hand, I work in theoretical areas like online and sequential decision-making, machine learning, and optimization. And I deploy these new theoretical ideas to applications like energy resource operation, carbon-aware computing, energy system planning and operation, and grid-scale energy storage. So many applications with energy and sustainability focuses. And I've also thought about some non-sustainability related problems like video streaming with Amazon Prime Video. And so the general research theme that I think about is if we have a decision maker faced with some problem in energy or sustainability, how should they incorporate AI and machine learning into their decision-making pipeline? So how can they take advantage of this machine learning, but also ensure robustness or ensure reliability? And so in this talk, I'm going to focus on the more specific question of how can we use AI and machine learning with varying strengths of a priori guarantees for reliable decision-making in energy? So there's a spectrum of different types of models and training methods out there. And so on the one hand, we have black box AI models. So this is like ChatGPT. You don't necessarily know how it's going to perform if you apply it to a particular problem. So it's sort of just black box. And on the other hand, you can apply some ideas in uncertainty quantification in order to get kind of post hoc uncertainty estimates or reliability estimates for a model. And this might give you a little bit more reliability. But ideally, what we want to do, if we can, depending on the problem structure and depending on how many resources we have, is train a model end-to-end with some notion of reliability in the loop. So say train a model to output uncertainty estimates that are optimal for a particular task, for a particular decision-making problem. And so I have work across the spectrum, and each of these buckets is important depending on what kind of setting you're in. Maybe you don't have too many resources to train a new model from scratch, and you just want to get the best possible performance out of the black box approach. On the other hand, maybe you really care about reliability, and you're willing to expend the resources to train a new model end-to-end. And so today, during the first part of my talk, I'm going to be talking about how we can incorporate black box AI or machine learned advice into certain online decision-making problems that model energy systems applications. And then toward the end, I'll highlight some ideas on how we can push more toward these end-to-end ideas. All right, so the motivation for incorporating black box AI into decision-making comes from a collaboration that we did with this company called Beyond Limits, which is basically an AI consulting company based in Glendale, and they do a lot of work with energy utilities. And so they were facing a problem where their industry partner was trying to optimize combined cycle cogeneration power plant operation. So in this problem, the plant operator or decision maker is faced with uncertainty, including the ambient conditions, so temperature, pressure, humidity, which influence the efficiency of generation, electricity demand, so how much electricity they have to provide to the grid, and also municipal steam demand. So the cogen power plant has to produce a certain amount of steam for local heating. And in response to this uncertainty, at every time step, say every 5 minutes or every 15 minutes, the power plant operator has to choose how much electricity they're generating on their gas and steam turbines, how much steam they're producing and sending to the grid for heating versus into their steam turbine for electricity generation. And once they make this decision, they incur some cost, which represents the fuel cost of operating the power plant at that particular dispatch set point. And this is a particularly challenging problem in the high renewables regime. So on power plants with a significant renewable variability, this requires more frequent ramping. So you need to change the dispatch set point of the generator more frequently, and this incurs degradation or loss of efficiency on the power plant. And a common approach to try to handle or anticipate this coupling between decisions resulting from this ramp cost is something like model predictive control. So you try to optimize your cost, including the fuel cost and ramp cost, over some look-ahead horizon. And usually when you're doing this, you're using some sort of forecasts about what the ambient conditions are going to be, say 15 minutes or an hour or 2 hours into the future. Now, the challenge in applying something like model predictive control in this setting is that in this power plant model, the fuel costs are complicated non-convex functions. So Beyond Limits had these non-convex neural network black box models for the input-output behavior of these power plants. And so it's intractable to solve model predictive control exactly, even with a moderate look-ahead window. The complexity grows exponentially in that look-ahead. And they were using heuristics in order to try to approximately solve this problem and get dispatch recommendations. But these were still slow and poor quality, and they were interested in trying to use AI and machine learning to basically speed up the solution to these problems and get better performance.
Can I ask, just in this case, what was the size of the state vector?
Yeah, the size of the state vector was somewhere around, I think, 8 state variables for each time step. And so over a look-ahead window of roughly 7 to 13. So say order of 50 to 100.
In the control vector?
So the state is the control vector.
Okay.
So they're not modeling any sort of persistent state over time. Just the decision they make is the dispatch set.
Okay. I see. Okay.
So this is where we came in. And so in order to model this problem, we turned to this model in the computer science literature called metrical task systems, or MTS. And you can think of this as a problem. Let me try to get rid of this real quick. You can think of this as a game between an adversary, which represents the power plant, and a decision maker. And so at each time step of the game, the adversary gives you some cost function ft, which maps from a metric space M to the positive reals. And after seeing this cost function, the decision maker chooses some decision xt in the metric and incurs what's called the hidden cost. So the cost ft of xt plus the switching cost. So the metric cost of switching from their previous decision. So this models the fuel cost and the ramp cost in the generator setting. And this game is repeated at each time step of the instance. And at the end of the day, the decision maker just pays the sum of their costs over time. And this problem goes by a number of names. I don't know why this keeps on fast forwarding through these. It goes by a number of names, including online optimization of the switching costs, smooth online optimization, and function. And it's worth noting that it also models other problems like data center operation, various logistics problems, and also video streaming. And the typical goal in designing algorithms for metrical task systems is to look for an algorithm with the smallest possible competitive ratio. And so this is the worst case ratio in cost or expected cost between the algorithm that you're designing and the offline optimal that sort of knows all of the uncertainty in advance. And just in terms of the state of the art in the literature, generally speaking, for metrical task systems, these competitive ratios depend on the size or the cardinality of the decision space. So if you're thinking about general finite end state metric spaces, it's going to be roughly growing linear in that dimension, or logarithmically in that dimension if you allow randomization. And for a class of problems known as convex function chasing, so you're making decisions in some vector space, you're faced with convex cost functions, and your switching cost is some norm. Generally, the competitive ratio is going to be linear in that dimension.
Here's a question. So your previous slide about motivating this total cost, you're looking at for each stage there is uncertain state, right? So in here, you're assuming essentially this uncertain state is generated as adversarial.
Yes.
Okay. So, but there is no like Markovian transition.
Yeah, there's no Markovian structure that we're assuming. And part of the reason for that, you might assume that there is some sort of structure in how the ambient conditions evolve over time, but we're also considering demand uncertainty and net demand uncertainty. And they're also interested in variants of this problem, including price uncertainty. So if the power plant is trying to optimize its profit over time. And so in those cases, there's not necessarily as strong of stochastic structure that we can leverage.
Sure.
So traditional algorithms for metrical task systems, because they're looking at this notion of the competitive ratio, this is a worst case performance metric. And AI and machine learning, because they can take advantage of data, can often do better. And so we're going to consider a model of this problem where we have an advice algorithm that at each time step, after we see the cost function ft, but before we make a decision, it recommends that we make some decision at. So this is like the output of a machine learning algorithm or an RL algorithm of some sort. giving us a decision that it says we should make. And then after we see that recommendation, we'll make our decision and incur our cost. And then in the next time step, we'll get another piece of advice, and so on and so forth. But the problem is that this AI advice might be bad. It might not be trained on the exact set of problem instances that we're going to see at test time. There might be distribution shift, there might be adversarial attacks. So how can we take advantage of this performance, even if the black box advice is potentially adversarial? So the intuitive goal of this work is really to bridge two different regimes, where on the one hand, traditional algorithms have strong worst case guarantees, but can't take advantage of data, and so have poorer average case cost. Whereas AI and machine learning can take advantage of data, can get better average case performance, but don't necessarily have worst case guarantees. So our goal is really to explore this Pareto frontier, trading off between average case and worst case guarantees. And so our general approach is going to be to take our black box advice algorithm, which is going to produce decision recommendations, and we'll also take some robust algorithm, which henceforth I'll refer to as Rob, and the advice is Ad, and we'll try to combine these algorithms via some meta algorithm in order to produce decisions which are both efficient, taking advantage of the AI and machine learning when it's good, but also robust. So intuitively, how should one of these efficient and robust algorithms perform if the advice is good? So consider a problem instance where the advice and the robust and our algorithm all start at some point. They're faced with some region of low hidden cost for the next time step. And we see that the advice moves here and the robust moves here. So the advice is sort of in this corner, the robust is hedging a bit more and being in the center. Well, we want to take advantage of the advice in case it's good. And so we should do something close to the advice, not super close in case it turns out to be bad. But then as we sort of roll this problem instance forward, we see, okay, the advice moved to the center of all of these low-cost regions, and it didn't have to incur too much movement cost. But on the other hand, if the advice is performing poorly, say it moves to this bottom right corner, then our algorithm should hedge a little bit and not move all the way, stick a little bit closer to the robust in the center of this region. And over time, we see, okay, the advice is incurring a lot of movement cost, so it's good that we stayed a bit closer to the robust, and we can sort of adaptively tune how close we stick to the advice versus the robust.
Excuse me, can you clarify a little bit on the visual? You say this is low cost region, and so how do you say the advice is poorly or good?
Right, so this is sort of the challenge. You don't know in this first instance, like when you see this first region, you don't know if the advice is going to be good or bad or not.
Yeah.
And so you want to do something that is sort of hedging between the advice and the robust. But then in the next time step, you see, okay, the advice incurred a lot of movement cost. The robust did not. So I can move a little bit closer to the robust. And then in the next time step, the advice also incurs a lot of movement cost. The robust incurs less. So you move even closer.
I see.
So the idea is somehow we need to design an algorithm that can adaptively tune how close we follow the advice versus the robust, and account for, basically in an online fashion, how each algorithm is performing. Does that make sense?
Yeah, and how this move be understood in the context of some application as you just articulated?
Right, so in the sort of energy system application, in the cogen power plant operation, the movement cost is the ramp cost. So say you're ramping a lot on one of your generators and less on the other generator, and with the advice, and then the robust is ramping the second generator, but not ramping the first generator as much.
Got it.
And so you play some decision that's in the middle, and you need to make sure that you can get to either decision, depending on which ends up being better.
Thank you.
All right, so we want a meta algorithm specifically that achieves what's called consistency. So we want our algorithm to obtain cost that's no more than 1 plus epsilon times the cost of some black box advice of our choosing. And we also want to obtain robustness. So that means that the cost of our algorithm should be a bounded multiple of the cost achieved by our chosen traditional robust algorithm. This is, all right. And the trade-off here should be tunable. So we're going to have some hyperparameter epsilon that basically governs how closely we want to match the performance of our black box AI advice, and in return, what our worst case robustness is going to be relative to the traditional robust approach. And this paradigm of robustness and consistency has seen a lot of recent interest in the algorithms and machine learning community. It's called Algorithms with Predictions, and there have been more than 250 papers in the last 5 or 6 years looking at this design framework for various online and non-online problems. So this is a very general framework for trying to integrate black box predictions or advice into decision making. So specifically in the case of metrical task systems or MTS, most prior work looked at special cases, including some of our own work. And there's really only one paper that considered the general MTS setting, and that's by Antoniadis and co-authors. And they basically applied off-the-shelf algorithmic approaches to try to obtain these dual performance guarantees. So on the one hand, they applied essentially a doubling idea to get 9 consistency and 9 robustness. And what this means is that in the worst case, you're going to be paying 9 times the cost of your black box AI advice. And the reason for this is it switches back and forth between the decisions of your advice and robust strategies very frequently. So it's incurring a lot of additional ramping cost effectively. And on the other hand, okay, maybe I'll switch to the other thing just because this is, yeah. Okay, just this. Sorry about that. It just keeps on fast forwarding.
Right. Great.
Okay, hopefully that works well. Should
The adapter's a little finicky.
yeah, okay. Oh. Was working.
There's no way we'd be able to do this without some IT issue.
Do you want to change to this adapter?
I think maybe let's just unplug it and plug it back in because it was briefly working. Okay. All right. Hopefully this helps now. All right. So where was I? I was here.
Maybe one question.
Yeah.
So you start at 9 consistent and 9 robust.
Yes.
Yeah.
How should we interpret it if I care about practical use? What does it tell me?
Right. So if you care about practical use, this is essentially saying if you want robustness,
Yeah.
and you feed in your advice algorithm and your robust algorithm into the strategy, you're going to be paying, in the worst case, 9 times the cost of your AI strategy.
Yeah.
9 times the cost that it incurs. And the reason for this is that the doubling idea is essentially saying, without looking at the performance in any sort of granular sense of the 2 different strategies, you follow the advice, and then you switch back to following the robust, and then you follow the advice, and you switch back to following the robust. And you can't really bias it in favor of one or the other in any meaningful way. So this is sort of leaving a lot of performance on the table if what you care about is getting bounded performance or close performance relative to the AI.
Hey, sorry, Nico, can you share your screen again on Zoom? Perfect.
Okay. All right. And so on the other hand, they also give a randomized algorithm that achieves what sort of looks like 1 plus epsilon consistency and robustness, but with an additive factor of d over epsilon, which depends on the diameter of the decision space and this hyperparameter epsilon. And essentially what this is saying is that you can, in the long run, closely match the performance of whatever's better between your advice and your robust strategy, but you're paying this very large fixed cost upfront. And so an important question is, can you actually take advantage of the problem structure in MTS to do better and get better, provably optimal trade-offs between taking advantage of your advice and getting robustness? So can we exploit problem structure to do better? And so one initial idea that you might have is to try to switch deterministically between the decisions of your advice and your robust strategies. And so what this might look like is you have your advice, you have your robust, and we define some switching algorithm that follows the advice for a little bit, and then switches over to following the robust for a little bit, switches back to following the advice, switches back, and so on and so forth. So can this kind of idea yield good consistency and robustness trade-offs? And so we can actually answer this in the negative. So it turns out that if you use a deterministic switching algorithm, that's just following this kind of strategy, if you want finite robustness, so finite worst case guarantee, your consistency has to be at least 3. And so this means in the worst case, you're still paying 3 times the cost of your AI advice strategy. So you're not fully able to take advantage of its performance. So if determinism doesn't work, we have to move to randomization. And so what this means is that at every time step t, we're going to choose some decision xt supported on the 2 decisions, one made by the advice and the other made by the robust. And so how should we specify a probability distribution on these 2 decisions at each time? So our basic idea is that we should set ourselves a consistency budget, 1 plus epsilon. And this is going to say, at each time step t, I want to make sure that the random decision that I make in expectation can guarantee me 1 plus epsilon consistency. And then subject to that consistency budget, I want to choose this distribution to be as robust as possible. So we should minimize some notion of cost of that decision. So how should this kind of algorithm behave? Going back to this geometric picture, we have the advice right here and the robust right here. This consistency budget effectively describes some set in the space of probability distributions that governs what decisions we can make while maintaining consistency. And then subject to being in that set, we should try to be as close as possible to the robust strategy. So how should we actually implement this? How can we update our distributions at each time to obtain consistency? And can we get robustness out of this? So we propose an algorithm, which we call DART, or Distance Adaptive Robust Weight Transport. And I'm not going to go too much into the details, but the basic idea is that it's a randomized algorithm that at each time step chooses the advice decision with some probability lambda t, the robust decision with some probability 1 minus lambda t, and it updates these weights based on some rules where if the advice is performing well, we should just follow it directly. And if it's not performing well, then we should decrease the weight that we assign to it using this complicated update rule. And eventually, if the advice is really not performing well, we'll be robust. And so we're able to prove that for any metrical task system and any epsilon greater than 0, DART is 1 plus epsilon consistent and has robustness that is exponential in 1 over epsilon. And so the basic idea here, even though the sort of DART algorithm framework doesn't look like this consistency budget that I described geometrically, the consistency is very easy to prove. So these updates are sort of designed to give you consistency. And so robustness is the hard part. And so you kind of have to prove how far astray bad advice can lead you and sort of bound your worst case problem instance. So you might look at this and ask, okay, so you can get 1 plus epsilon consistency, so take advantage of your machine learning as much as you want, but in exchange, your robustness is exponential in 1 over epsilon. So that's seemingly exposing you to very poor worst case performance. Is this actually necessary? And it turns out that it is. So we can also prove a lower bound showing that for any 1 plus epsilon consistent randomized algorithm for MTS, it has to be exponentially robust in 1 over epsilon. And the idea sort of takes place on a particular construction of a problem instance, so a specific metric space where The advice and robust start at the same point. The algorithm starts at that same point. And then the robust moves a little bit to the left. The advice moves a little bit to the right. And in order to maintain 1 plus epsilon consistency, a 1 plus epsilon consistent algorithm has to send most of its probability mass to the advice. And then at each time, the advice doubles its distance from the robust. And still, to maintain this consistency, it can't send too much of its weight back to the robust strategy. And so at the end of the day, the advice has moved an exponential distance away in 1 over epsilon. Now, this is kind of a contrived problem instance. It's a very particular problem setting. So even though this lower bound is synthetic, can we actually show similar lower bounds in other settings? Well, it turns out that we can. So in the setting of convex function chasing, so we're making decisions in the vector space, all of the functions that we see are convex, and the switching cost is an L1 norm, we have the same lower bound, showing that if you want to be 1 plus epsilon consistent, your robustness is going to be exponential in 1 over epsilon. So again, this is pretty pessimistic, but thankfully there are some settings where you can do better than this sort of worst case exponential performance. So if for all time steps, the advice and robust decisions are never further apart than some distance d, then Dart is 1 plus epsilon consistent and has robustness that is 1 over epsilon plus an additive term that depends on this distance bound d. And so you might compare this to the Antoniadi strategy that I mentioned earlier that also had a d over epsilon additive term. How this differs is that it's a post hoc analysis, so you don't actually need to know this distance in advance. And so in an instance-dependent sense, Dart can do better in terms of robustness, and you don't have this additive term on the consistency. You're still fully taking advantage of your machine learning performance. And something else that I'll briefly mention is that a well-known problem in the theoretical computer science literature known as K-server, Dart can also achieve better trade-offs in this setting. So 1 plus epsilon consistency and K over epsilon robustness, where K is the number of servers that you're moving around in the decision space. And the reason for this is a structural property for the optimal solutions of K-server. All right, so that's the theory. I'm going to move back to the experiments. So we're working on a real-world cogeneration power plant model that Beyond Limits gave to us. And I'll briefly plug SustainGym, which is a reinforcement learning benchmark suite that we put together, which included this cogeneration power plant model, as well as a few other models, I think, of data center operation, HVAC building operation, electricity markets, and maybe 1 or 2 more. And so we developed this model in partnership with Beyond Limits. We have ramp costs, which are just weighted L1 norms, and non-convex fuel costs, which are just black box neural networks that Beyond Limits gave us. And again, Beyond Limits wanted to try to incorporate forecasts and try to get better performance via something like MPC, but classic MPC was too slow due to this non-convexity. And so we trained a machine learning model as our advice to choose dispatch decisions XT at each time step using look-ahead predictions of ambient conditions. And then our robust strategy, which we're using as a baseline, is just a greedy strategy that minimizes the instantaneous fuel cost at each time without considering ramping at all. And so when we look at model predictive control, it takes on the order of about an hour in order to produce dispatch decisions. But on the other hand, both the greedy baseline and Dart as a result are about 100 times faster. And so greedy is much faster, and Dart really only comes with minimal overhead from the machine learning, because making the machine learning-based decision only requires a feed-forward pass of a neural network.
Sorry, can you say something about how the machine learning model is trained? Like, are you solving the full-blown non-convex MPC just asynchronously, getting the solutions and using that to train?
So we're doing an unsupervised approach where we're training the machine learning model to produce decisions and evaluating the loss of those decisions and using that loss differentiating through to update the ML model.
Okay, I see.
And so Dart and our strategy is not only faster than the classic MPC-based approach, but it actually ends up performing better than both the machine learning approach and the greedy approach. So here on this plot, everything is normalized by greedy. So greedy is just 1 on the normalized cost axis. And as we think about increasing prediction noise, so adding noise to the predictions used by the ML model, it goes from performing better than greedy, so roughly 80% the cost of greedy, to performing worse, so like 1.2 to 1.3 times the cost of greedy. And so when we combine the ML and the greedy approaches via our algorithm DART, it's actually doing better and smoothly transitioning between good performance when ML is performing well and good performance when greedy is performing well. And so somehow the fact that it's doing better than both says something about how on an instance-dependent basis, DART is learning, whether ML is better or whether greedy is better for the particular problem instance. So, all right, so those are the experiments. Any questions before I move on?
Can you explain why you call it greedy as a robust approach, or for robust you can arbitrarily choose some other algorithm?
Yeah, so the robust can be anything. Also, the advice can be anything. So the advice doesn't have to be ML. It could just be a standard MPC algorithm if that's tractable that you want to combine with something else. But in this case, we use greedy because that was one of the baselines that Beyond Limits was working with. And this is sort of a fairly classic single shot economic dispatch strategy.
Okay, so when you call it a robust algorithm, you do not impose some normative property of that algorithm.
Right. Yeah. So for all intents and purposes, you can apply DART to any algorithm, even if there's no, say, robust strategy in the theoretical sense.
So arbitrarily pick two algorithms, you can kind of like some combination of them, but outperform both of them.
Yeah.
So why is in this case greedy the robust strategy?
Sorry, greedy.
So for example, let's say you have a future prediction and you assume that the future instance is selected by some adversary. But is greedy the optimal decision for against the adversarial selection of future?
Greedy is not optimal, but in this particular instance, we're in a vector space decision setting. And so there's actually no robust in the competitive sense out. So the reason we use greedy is because under some assumptions, if you impose certain structural assumptions on the cost functions, greedy does actually have a competitive ratio. But that's not something that we can necessarily verify because the costs we see are non-convex and black box. All right, so that is all for the experiments. So just to recap briefly, DART delivers best of both worlds performance for measurable task systems, and in particular, this cogeneration operation application. In what other applications can this strategy of trying to take advantage of black box, AI, or machine learned advice enable better performance for energy and sustainability problems? So one other application I want to highlight is that of carbon-aware temporal load shifting. So think about a data center that is serving various workloads from its users. It's connected to the grid, and when the sun is shining, we're happy because the grid carbon intensity is low, or you're using clean energy, not using too much carbon. But then the clouds come out, the solar energy decreases, and all of a sudden, the grid electricity is much dirtier. So what the data center can choose to do, if it has extra capacity or if it has flexibility in when the workloads are actually completed, it can checkpoint the job, shut down some of its servers to save on carbon, and hopefully later in the day, there will be more sunshine or more wind that can start up those jobs and finish them by the deadline. So more generally, we can think about the problem of carbon-aware spatiotemporal load shifting. So here we have a user that sends some workload to a server where there's nice solar power available, so clean grid electricity. But then the clouds come out, and so that server might choose to checkpoint the workload, incur some temporal costs because it comes with overhead of doing the checkpointing, saving, and then turning the servers on and off. And you can also choose maybe to shift that workload to another server. So migrate the job to another server in a location where there is cleaner energy on the grid. But at the end of the day, you have to finish the workload by some deadline, give it back to the user. And so you can model this kind of problem as an online optimization problem that looks a lot like MTS with some changes. So we can think about minimizing a sum of carbon costs for the amount of carbon in the electricity that you're using to power the servers, a multi-scale switching cost that accommodates both the spatial switching cost of migrating jobs from one location to another, as well as the temporal cost of the overhead from turning a server on and off. And you also have this deadline constraint where for a particular workload, you need to finish it by the time that you said you would to the user. And so there's this additional structure, the multi-scale structure and the hard deadline constraint here. So it's a bit different than the setting we consider Dart in. Can we still leverage black box AI and machine learning to get better performance in this setting? Because of the fact that it's much higher dimensional, we have a lot of uncertainty to deal with. Can we get better performance here?
So how much is the switching cost in this case if you are shifting the workload? Is it negligible or is it?
I don't think it's negligible. I can't say like a specific percent, but my understanding is that for shifting, say, across continents or across the country, it's
Maybe it could be you're switching to a power grid network that has higher electricity costs, but lower carbon,
right.
and that could significantly impact the operating costs.
Right. So you can also incorporate that either into the hidden cost or maybe as some sort of opportunity cost in the switching cost. Yeah, so there's multiple ways that you could model that. Yeah.
I mean, maybe you could also save money with it, right? If you just distribute your job, or let's say like when the sun is not shining anymore, like your PV farm doesn't generate like enough power, so maybe you have to buy electricity and that comes to a big cost. So you basically try to send your data to another data center and calculate your results there. And if the electricity price there is lower, then you might be able to save money, right?
Right. So I guess more generally, you can think about a hidden cost function at each time that's maybe not just carbon, but also carbon plus electricity costs weighted in some way, depending on how much you care about each.
But did you also take this into consideration? Just like, have you some thoughts about that?
So sorry to interrupt. Maybe 5 minutes for presentation.
Okay.
Then we can go to Q&A.
Yeah. Okay.
We can discuss later.
Yeah. So just to, I guess, briefly motivate again, can we leverage black box AI and machine learning in this problem setting as well? So revisiting the consistent set, remember that we specified the set of decisions that we can make where we maintain the 1 plus epsilon consistency relative to our advice strategy. And subject to this constraint, we want to be as robust as possible. So how can we actually implement this for this more general problem? And so we propose an algorithm, which we call ST-CLIP, or spatiotemporal consistency limited pseudo cost minimization. There's a lot going on here, so I'm not going to go into any details. But the idea is basically that we have the pseudo cost minimization at each time step, where basically we're minimizing our instantaneous cost of our decision, subject to some regularization that basically makes sure that we're making enough progress at each time step toward our deadline constraint, right? Because you don't want to not make any progress, and then at the end of the day, you haven't completed any of the workload, and you need to complete it at very high carbon costs or very high electricity costs, maybe. And when we're doing this minimization, we impose a consistency constraint that is effectively encoding the requirement that at each time step, we need to make sure that we're always 1 plus epsilon consistent relative to our black box advice strategy. And that strategy is basically giving us a recommendation of, hey, you should schedule these workloads at these locations and migrate these workloads from here to there. And so we're able to prove that ST-CLIP achieves 1 plus epsilon consistency and robustness that is log n, where n is the number of data centers or locations, times gamma epsilon, where gamma epsilon is something very complicated that I won't get into. And also this trade-off between robustness and consistency is optimal up to this logarithmic factor in the number of locations.
Sorry, gamma, I know you said you wouldn't get into it, but gamma is a function, some transcendental function of epsilon?
Yes.
Okay. So it's not, you're not saying exponential per se.
No. Yeah.
Yeah. Okay.
Sorry, the epsilon is a parameter of gamma.
Okay.
Yeah. And so in a case study on carbon-aware spatiotemporal load shifting using real-world carbon traces as well as data center traces, this is showing a CDF of the empirical competitive ratio. And effectively, STClip is able to perform better than any of the other baselines that we compared against for doing this spatiotemporal load shifting. All right, so I think I'm limited on time. And so in the interest of not going too much over time, I guess, do I have 5 minutes or?
Yeah, it's best if you can finish it.
Okay. All right. So in the previous part of the talk, I was discussing how we can incorporate black box AI and machine learning into decision making with worst case guarantees. But at the beginning, I highlighted this whole spectrum from black box to gray box to end-to-end strategies. And there are many different considerations that you have to consider when deploying machine learning in the real world. And so, how should you actually design new algorithms and AI and machine learning training procedures that can prioritize these criteria like risk or uncertainty quantification or different notions of reliability? So I don't have time to fully go into this, but I just want to give a brief teaser where if we're thinking about problems where you're trying to control risk or trying to control uncertainty in decision making, such as in grid-scale energy storage, where battery operators need to manage the uncertainty and risk that they face when deciding whether to buy or sell electricity from the grid. Oftentimes, these decision-making pipelines that battery storage operators use look something like the following. So they have some weather data that they're going to try to use to predict electricity prices. And so they use a machine learning model to predict electricity prices and then somehow construct an uncertainty set omega x that contains the true electricity price with some specified probability. And then they want to feed this uncertainty set into a risk-aware optimizer, such as a conditional robust optimization problem, where basically they're trying to minimize their losses subject to operating constraints over the worst case price in the uncertainty set that they've constructed. And after solving this problem, they obtain some battery charge or discharge decisions, C star, and then they deploy these decisions in the real world. The uncertainty is realized, so the price is actually revealed, and they incur some task loss. And so their goal is to minimize this expected task loss, subject to making sure that they're actually obtaining calibrated uncertainty estimates, so they're hedging their risk and using that uncertainty estimate in this risk-aware optimizer. So the typical approach in practice is a two-stage approach called estimate then optimize. And so the first thing that they'll do is estimate this uncertainty set from data. And oftentimes they're using something like a restrictive uncertainty set estimation representation, like a box or ellipsoidal uncertainty set. And then they'll calibrate this uncertainty set using something like conformal prediction. And I think I have a slide going into conformal prediction, which I'll fast forward through. And so there's a challenge here where if they're using these restrictive uncertainty estimates, can they do better by learning more flexible representations of uncertainty? And then after they've learned this uncertainty, they use it to optimize their decisions for the downstream decision-making problem. But this means that their learning of the uncertainty isn't actually informed by the loss that they incur at the end of the day. So there's this question of how you can actually train the machine learning predictive model and train these uncertainty estimates in a way that is end-to-end and informed by this downstream task loss. And so I think I need to finish up, so I'm not going to get into this, but the slides I think will be online, and if you're interested, feel free to ask me questions. So I'm going to zoom forward to the end, where basically I just want to finish by highlighting that there are growing challenges across energy and sustainability. Again, ranging from the uncertain variability of renewable generation and novel resource types on the grid, like battery storage, enhanced geothermal, many new risks that we're facing and growing risks like wildfire risks or asset failures.
Is that a prediction from your apartment or something?
That is from the Caltech campus. Yeah. Increasing demand due to electrification and AI data centers, and also many other considerations beside the sort of standard carbon and sustainability, such as public health or human impacts of these technologies that we need to think about when we're planning and operating energy systems. And so all of these challenges motivate new frontiers and algorithms for reliable AI and machine learning. And I'm very interested in sort of following up on my previous work, as well as, jumping forward in new directions, such as designing AI and machine learning strategies that can satisfy constraints and give safety guarantees, developing new machine learning for optimization strategies to help tackle some of these hard, large-scale, non-convex optimization problems in power system planning and operation, and better learning and optimization for multi-objective problems when we're thinking not just about economic cost and efficiency, but also carbon emissions, downstream public health outcomes, and so on. And so I'll briefly pitch that, this year I am a Stanford Energy Postdoc Fellow, but I will soon be moving to Johns Hopkins, and I'm hiring PhD students and postdocs. So if anybody is looking and interested, definitely reach out. And also if you're a PhD student on the job market, Hopkins is hiring across many different fields. So definitely consider them. And with that, thank you for listening. Happy to take questions.
Thank you, Nico. And maybe you can turn off your audio and I'll turn on the meeting hall, so that might be bad. Yeah, so people on Zoom, you can still hear me, right? Great. So, Professor, we're going to just moderate the discussion.
Okay, so, do I need to follow the steps?
You are the moderator.
Okay, so then I won't follow the steps. Thanks for a great talk. I'm actually very curious about the part that you omitted, which is about the, give some insights about what kind of algorithm that end-to-end learning is about?
Sure, do you want me to go through the slides?
However you like, so.
Yeah, I'll just do that.
Just a small flavor.
Easiest.
It was a very effective amuse-bouche, you got us.
Yeah, you got us hooked and then you
Yeah.
decided.
We got a little taste, we want more.
Yeah.
Okay.
So, right, as I sort of highlighted in this overview, there's these two questions about learning more expressive uncertainty sets, as well as how we can learn the uncertainty estimates in a way that's informed by our downstream task plots. And so the first solution is that we can actually learn general families of convex uncertainty sets using what are called partially input convex neural networks. And so this is a parameterization of neural networks, where if we say that S theta is a PICNN defined by these equations, then under certain parameter assumptions, so namely some parameters have to be positive, then S theta of x comma y will be convex in y for each x. And so that means that if we define the uncertainty set omega of x as the y sublevel set for some level q, then that will be a convex set. And depending on what q is, we'll either have a very small set or a very large set. And I skipped the slide about formal calibration, but basically if you set this q correctly, you can obtain coverage. So you can make sure that the uncertainty set omega of x actually contains the true price y with probability 1 minus alpha for whatever alpha you choose. And so we can calibrate the set very easily using the terms of the tools of conformal prediction. And this is nice because PICNNs can represent general partially convex functions. So you can represent general families of convex uncertainties. And so this means tangibly, instead of just having box uncertainties or ellipsoidal uncertainties, you can learn sort of more funky uncertainty sets. But of course, one question you might ask is this kind of uncertainty set tractable to optimize over in this kind of robust optimization framework? And it turns out that the answer is yes. And so we prove a theorem showing that you can reformulate this min-max problem in a similar way that you would do for robust optimization over ellipsoidal uncertainty or polyhedral uncertainty into a tractable convex.
So when you do this, like your neural net can only provide you like an oracle of what's the convex uncertainty set given an input decision that you currently have, right? It doesn't really have this like functional function expression. So your optimization does not rely on knowing about the characterization of the convex set.
I'm not sure I understand the question.
So for example, in this most classical way of doing this robust optimization, people come up with these polytopes, right? And then you can flip this problem into, okay, I'm going to make decision against the extreme points of these convex. So that actually requires a lot of characteristics of the uncertainty set, which your neural network cannot provide.
So effectively, the way that we prove this theorem is showing that you can apply the same ideas that you would in
Okay.
getting a tractable counterpart to
Okay.
the min-max robust problem
Okay.
over, say, polyhedral uncertainty.
Okay.
You can apply those same techniques when you're using PICNN uncertainty. And so that means because PICNNs can represent general families of convex uncertainties, you can approximately do robust optimization over general convex uncertainty sets.
So does your neural network so what is the output of your neural network?
It doesn't represent anything in particular. Essentially, the neural network takes as input X, which is the
Okay.
input of the ML model. This is something known like the weather data, and Y, which is the price, which is unknown.
Okay.
And so we see X, that gives us an uncertainty set as the Y sublevel set.
Okay.
Of our score
Sure.
function
So it outputs the sublevel set of Y the sense. Okay, great.
implicitly.
Okay, great. So there is also another line of work that looks at this thing completely like end to end, like without really even solving the optimization problem as this formulated way, but just, for example, using a policy gradient on the decision part, and then iteratively goes back to the uncertainty set to try to find, for example, the extreme case that is against the current decision making. So I was wondering, like, have you thought about the comparison of these? This like even more end-to-end kind of approach.
Yeah, I think we haven't thought about that comparison too much, just because I'm not super familiar with that work, but in this case, because we are calibrating the uncertainty sets, and I guess that's one detail that I sort of glazed over. But because we're calibrating the uncertainty sets to make sure that omega of X contains the true price Y with probability of 1 minus alpha, we get this sort of theoretical guarantee that we are actually doing better than, or at least as well as the worst case uncertainty with probability 1 minus alpha. And so I'm not sure if you just end to end with the decision, whether you can have that same theoretical guarantee.
That approach doesn't have theory.
Maybe we should open some
Okay,
question for the
yeah.
student. Any
Go ahead.
question from the audience?
Before I call your name. Sorry.
It's your right.
No, Scott.
Well, following Monsi's questions, yeah, now I'm curious, this line of work, do you categorize that in the gray box or in the end-to-end category?
Yeah, so I would characterize this in the end-to-end category because of the slides that I haven't actually shown yet, where we do answer the question of how to use the task blocks to basically backdrop through the entire decision.
I see, that was, I was gonna ask if then because you have this partial convex, it allows you to take gradients backwards
Right,
through the whole structure.
right. So effectively, if you just did the PICNN, it would be in the gray box. So you can learn more general uncertainties. But then the other component of what we provide in this work is an end-to-end learning framework, where basically when you're doing the calibration of the uncertainty set, that is something which is not necessarily differentiable a priori. And so prior work typically, I guess I should maybe go into a little bit more detail here. So I'll just highlight this slide that I had about conformal prediction. So let S theta of xy be a nonconformity score. This is just any function of x and y. And define omega theta of x as the set of y, which are in the Q sublevel set of S of theta with fixed x. So this is how we'll parameterize our uncertainty set. We basically want to choose Q to make sure that we have calibration or coverage at level 1 minus alpha. So to make sure that omega of x contains y with probability 1 minus alpha. And so split conformal prediction is this very powerful and very general methodology for choosing Q. And the way that it works is you have some held out calibration set, decal. So this is a set of XY pairs. And as long as these XI-YI pairs and your sort of held out test point are IID or even more generally exchangeable, if you set Q to be the empirical 1 minus alpha quantile of S's value on your calibration points, then you have the coverage property that your held out point, Y, is going to be in the uncertainty set around X with probability about 1 minus alpha. And so effectively, you're doing a data-driven distribution-free way of calibrating your uncertainty set. And this depends on being able to compute this empirical 1 minus alpha quantile of your score function values, SI. And so that requires sorting them into smallest to largest values and choosing approximately the 1 minus alpha index small. So why do I mention this? Well, because if we want to differentiate through the calibration procedure, this sorting procedure is going to be a problem. Because you can't differentiate through a sorting procedure. This is a discrete procedure. And so previous work that tried to define a differentiable conformal calibration methodology used differentiable approximate sorting, but this is not necessarily aligned with the actual procedure that you use in conformal calibration. So what we make notice of is the fact that with high probability, or with probability 1, perhaps, you can differentiate through that empirical quantile. And so you can actually compute gradients through this conformal calibration step and include a trend trend. And so you can differentiate through that step. This conditional robust optimization problem, because we can translate it into a convex counterpart, we can implement that as a differentiable convex optimization layer, differentiate through that. And so we can compute the gradient of the task loss with respect to the model parameters, which parameterize this uncertainty set, and learn that in an end-to-end decision-focused fashion. That's the bits that I didn't get to.
We still get to going present it.
Yeah. Thank you, Nico. Thank you again. Maybe our seminar stopped now. And before we end, let's introduce the next speaker. Can you go to the slide and she's with us? So I just hand to you to introduce yourself and tell us why you must come next week.
Oh my God. I think you just handle your job to me.
So is there a slide?
Oh, I was thinking that. Okay. No, yeah. You just introduce yourself.
Okay.
Directly.
Okay.
I'm sorry.
Okay, it's fine, it's fine. Hi everyone, I'm Jo Fu. I'm a final year PhD candidate in transportation engineering at UC Berkeley here, affiliated with Berkeley ITS, Institute of Transportation Studies, and there, Berkeley Artificial Intelligence Lab. And I develop learning and control algorithms and also modeling tools for distributed parameter systems with a focus in mixed autonomy, which is where like automated and human agents coexist in the system. And for next week, the talk, I will firstly talk about a really interesting project that we did where we use a small portion of automated vehicles to impact the surrounded human-driven vehicles to smooth the traffic flow for the whole systems. And we did like a 100 automated vehicles field test, which is, I think it's the largest mixed autonomy field test in the history. And through that project actually motivates me to kind of dive more into how we can obtain a better like traffic dynamics using physics-informed machine learning. So I will, in the second pillar of the talk, I will introduce the neural finite volume method that we created to get more accuracy and scalability to model the traffic dynamics. So please join me for next week, and I promise it will be both theoretical div and also have a broader real-world impact. Thank you.